Today we're going to look at the polar coordinate system. This is a different coordinate system than you have graphed on before. You are familiar with what we call the Cartesian coordinate system. That's the one that has the x-axis and the y-axis. That was developed by René Descartes. It comes from Cartesian, comes from the name Descartes, named it after himself. That was in the 1600s. And once he developed this coordinate plane, then Isaac Newton came back and developed about 10 other ones. I learned that from Google. And one of the 10 he came up with was this polar coordinate system. So it's kind of an adaptation from this x and y axis with the grid that we graph on. But we don't look at it like it's a grid anymore. The polar coordinate system is a plane, a geometrical plane, that has a point at the pole. It's kind of like the origin right there. Right here's the pole. And the polar axis, which is really just this part of the x-axis. Each point in the plane is assigned polar coordinates, and those polar coordinates aren't like an x and y value. If you were to plot a point, it would have a coordinate that would designate the r value. That's the radius, because its polar coordinates are kind of like on a circular system, kind of like a unit circle idea. And the r tells you how far out to go from the pole. It's your radius. And theta is how far you've wrapped around to get to that spot. Not an x and a y, but an r and a theta. This is what the graph looks like now. You can see it's not like a grid. Well, it sort of looks gridish, but it's more like when you think of radar or that kind of thing. You're looking at these rings that come out, and those are like your radius. That designates how far out you're going to go from the pole. But you can also see there would be like some angles created, and that's the theta part. Let's try plotting a few so you can see what's going on. On this particular example, this first point P, the 3 is the r value. That tells you how many, that's your radius, that's how many rings out I'm going to go. And the angle that's going to get created is 4 pi over 3. To plot this, I have to think I'm going to be on the third ring out at 4 pi over 3. And we're doing lots of unit circle. So 4 pi over 3, you have to kind of look at what this is marked by. I have this little mark here and I have this little mark here, just to evenly distribute these, but those are not angles off the unit circle. This is like your 30, your 45, and your 60. And then these would be angles that we don't specifically know. But 4 pi over 3, I know where that's at. That would actually be this angle right here. Okay, I shouldn't have put that dot there because it's not really a dot. That's how far around I go, and then I go 3 rings out. Right there is point P. All right, let's try again. Q. Now this is going to happen at the angle pi over 3, but notice that my r value is negative. Think when we did vectors, what did you have to do when you subtracted a vector, when we were drawing it? Remember that you'd go the exact opposite direction? Okay, same deal here. Point Q, you're going to go around to pi over 3, which is right there. And instead of being on the second ring there, you're going to go the second ring in the exact opposite direction. So you're going to land right here. Right there would be point Q. All right, last one, point R. This one, the R value is positive. That's good, but this time the angle is negative. Well, think unit circle. Negative angles are just like they always have been. It just means you're wrapping backwards. If I'm going to be on the 5th ring out, right here, but I'm going to wrap backwards pi over 2. It's going to land right here. And that's point R. Now, each one of these coordinates designates exactly one point. If you were going to go graph those 3 points, you would have to plot them exactly like I did. But if I actually had the points already plotted and ask you to write the coordinates for it, you may come back with something different than what I had originally listed. For instance, can you think of another set of coordinates for point P? All right, this point here. This was the one where we said it was 4 pi over 3 and it was 3 rings out. Got it. But couldn't we have maybe, instead of gone to 4 pi over 3, could we maybe have gone to pi over 3 and then backed up the 3 just like we did for point Q? That could be another set of coordinates. I could have gone just to pi over 3. I kind of sometimes think of that backwards. I think of the angle first and then decide if my r value would be positive or negative. Instead of it being this positive 3, I could make it a negative 3, and it would land in this same spot right here. Different set of coordinates, same point. All right, you do that for r. See if you can come up with another set of coordinates for r that are different than this, but would still land right there. I'll give you a minute to think of it. Okay, probably the obvious one would be to quit using the negative angle. Don't use the negative angle. Go positively all the way around to there. You might have come up with a 5 and gone with a 3 pi over 2 instead of the negative pi over 2. Okay, you might also have, instead of, and tied it back to what we did over here, think about the angle. Think about the r for being negative. Maybe if you only went to pi over 2, whoops, I'd be out here at 5, go over here to pi over 2, but instead of having a positive r value, you have a negative r value and it shoots you down this direction, exactly opposite of where you want to be. You might have chosen then a negative 5 with a pi over 2 angle. That would have worked as well. Now, if you were feeling really fancy, you could have done a negative angle, but not stopped here, gone ahead and done the negative angle all the way back up to here. And then since that's not where I really want to be, I want to shoot it back down through here, made my r value negative as well. You might have written negative 3 pi over 2 for your angle, but had your r be negative as well. That third option that you might have written would have been having the negative 5 and the negative 3 pi over 2. There's 4 possibilities that you could come up with just by going positive or negatively. Now I could sit here and I could wrap around and sit there and get a whole bunch, an infinite number of different possibilities, but there's kind of 4 basic ones that you can come up with. One where they're both positive, one where they're both negative, and then angle negative, radius negative. There's 4 different ways to do that. So you could do that with all of these. We don't necessarily always use all of those, of course, but you need to be able to, if I give you one, could you come up with some others? Could you locate it on a graph? Understand what's going on with those positives and negatives. Now, remember I said that this is an adaptation of Cartesian coordinate plane that you've been graphing on for years. Well, there's a conversion between those two. We can get from the nice XY axis business to the r theta if we kind of tie them both into the same graph. I'm going to put in my x and y axis here, got that, but I also have my r and my theta drawn within the same graph. This is my point way out here. I can think of that point as over x up y. That's the we call it the rectangular coordinate system because it has a grid. But I can also think of this point as a radius measurement along with an angle that tells me how far to wrap around. If I draw this as a triangle here, there should be several relationships that you could tell me about that would kind of convert between r's and x's and y's and thetas and all of that, just from what we've learned in trig. Okay, so when you look at that picture, can you write me an equation? Any equation of something that you have learned, I don't know, in the past several months. Write me an equation. All right, There's 4 that come to me just right off the top of my head, just simple little things that you could come up with this. One thing with the theta in there, I see some SOHCAHTOA stuff that I could do. And with SOHCAHTOA, I could come up with 3 different equations that could work. I'm going to write these because I don't write very neatly on this app, so I would write these if I were you in the little box. I'm going to write them off to the side so it doesn't get as messy. You should be able to look at that and recognize, oh, I could do, like I said, SOHCAHTOA. I know that the sine of theta would be y over r. Now I wrote that, but I'm going to kind of clean that up a little bit. I'm going to get rid of the fraction on it, so I'm going to multiply both sides times r, and then I would have y is equal to r sine theta. Okay, I could do cosine. Cosine theta would be adjacent over hypotenuse, and again I'm going to get rid of the fraction, so I know that x could be equal to, or would be, r cosine theta. This should remind you a little bit of vector stuff that we have done. Let's try another one. What about tangent of theta? Tangent of theta is equal to opposite over adjacent. Now, for reasons I'll explain later, I'm not going to change that one and get rid of the fraction. That takes care of my SOHCAHTOA. There should be one more thing that you could come up with that, and that's just thinking some Pythagorean theorem. Would you agree that x squared, well, I'm going to write it over here, x squared plus y squared is equal to r squared? And when I write it in the box here, I'm going to change it up. I'm going to put the r squared on this side. Those 4 rules are what we can use to convert anything from rectangular to polar or vice versa. Which direction you're going kind of will determine which of these equations you want to use. I've written this, the way that I've written it, I've put rectangular stuff here, all the polar stuff there. Rectangular here, polar stuff here. These 2 are going to be used, if you know the polar stuff, you could go convert it to something rectangular. If you know the r and theta, go find the x and the y using these 2. But if you already know the rectangular, you know the x and y, then you could go figure out the theta. If you know the x and y, you could figure out the r. And that's how you're going to convert. If you want to go one way, you use these 2. Go the other way, you use those 2. All right, I kind of rearranged these 2 so it goes x and then y, but the same 4 rules there. So this time I'm going to go from polar to rectangular. That means that I already know r and I already know theta, and I want to turn it into an x and a y. Just for the fun of it, let's go ahead and visualize what this point would look like. It is a negative 200 degrees, so you're going to be backing up. There's negative 100, negative 200 somewhere right here. You're going to be 2 rings out. That point is going to plot somewhere around here-ish. What I'm going to do is I'm going to find the x and y coordinates if that was on a Cartesian coordinate plane or a rectangular coordinate plane. I know r and theta. That means I could do this real quick and I could do this real quick and find my x and my y. If I take 2 times the cosine of negative 200, now 200 or negative 200 is not a unit circle thing, so we'll be going decimal on these. But it is in degrees, and they won't always be, but this one is, so check your mode real quick and make sure that you are in degree mode. And then to find the x coordinate, I know that I'm just going to take 2 times the cosine of negative 200. I got a negative 1.88, we'll say. And then do the same thing. Do your y is going to be equal to 2 sine of negative 200. And I have y equal to 0.68. Now my final answer should be answered in the same way that they have it answered. P is going to be an ordered pair, but it's going to be a rectangular ordered pair. Negative 1.88, 0.68, and then check that. Does that make sense for where we plotted that? I'm negative 1.68 up 0.68. Should make sense. Just converted from polar to rectangular. Now let's practice using those rules going the other way. What if I gave you the rectangular coordinates? Can you tell me the polar coordinates? Again, let's start off and just think of what's going on, where that would be plotted. I'm left one, up one, somewhere right there. Okay, let's see if we can make that happen for polar coordinates. This time, I already know my x and my y. If you know your x and your y, then these two rules would be better. I know x and y, I can solve for r. I know x and y, I can solve for theta. I'm going to start with, I guess I'm going to start with my r, actually, because that comes first as I write the ordered pair. R squared is going to be equal to negative 1 squared plus 1 squared, which is really just 1 plus 1, so r squared is 2, square root it, r is the square root of 2. That's the radius, that's how many rings out I would plot, which of course means I'm going to fall between a couple different rings. Let's do the same thing, let's find theta. Tangent of theta is going to be y over x. The y is 1, the x is negative 1. I'm going to do inverse tangent, negative 1. Now since we're in degree mode, you're going to get a nice answer, but I'd like for you to not have to even use your calculator on that. Do you know when is tangent negative 1? Okay, well, if you do that, let's go ahead. I guess I'm going to go ahead and type it in. So I'm going to do second tangent negative 1. Oh, looky there, I got a negative 45 degrees. Let's think about that for a second. Negative 45 degrees is right here. Is that where my point is? Nope. But remember that when you do inverse tangent, it always gives you angles over here. So you got to use your brain over your calculator and say, I want the one that's over here, which would not be at negative 45, but would be at 135. Then my ordered pair is r comma theta, root 2, 135. Did you know that that was going to fall right there at a 45? Ideally, you knew if you're over and up the same amount, that's falling right at the 45 degree mark. All right, got to know these 4 formulas. This is something you're probably going to use enough times you're going to get the hang of what those 4 rules are. Let's try it now where we are doing more than just plotting points and converting points, but just like when you started off plotting points on a rectangular coordinate plane in, probably middle school, it advanced on to where you started plotting and graphing equations, and it started off linear equations, then it was quadratics. Okay, so that progression is going to happen the same thing on the polar coordinate system. Now that we can do points, let's do equations. We'll go both ways. This right here is what we would consider a polar equation because it has like a theta and an r in it. This is a polar equation. We want to graph or convert this into a rectangular. Some things convert real nicely between polar and rectangular. Some things do not. Let's see what happens with this one. All I'm going to do is I'm going to try to switch this r and theta into an x and a y in some way. What I'm going to do on this first one, I think, is go ahead and think of this cosecant theta as 1 over sine theta. I'm going to switch this to 5 over sine theta. And then I'm going to get rid of the fraction. I'm going to multiply both sides times sine theta. What I end up with is r sine theta equals 5. All right. R sine theta. Isn't r sine theta just y? Could I just get rid of this and call it y? Oh, yes, you can. Y is equal to 5. What does that look like on a rectangular coordinate system? Remember, that's like Hoivux, if you learned Hoivux. Y equals 5 is just a horizontal line. It's a horizontal line at 5. On our rectangular coordinate system, you're going to see that as just this horizontal line. We're going to do more graphing stuff tomorrow, so we'll look at how does that really look then when you put it on the polar coordinate thing. Well, it's still going to look just like that, but we'll talk about how it plots it later. Today we're kind of just looking at things algebraically. How do you convert back and forth? All right, so let's do another example. On this one, you can see it's already rectangular because it has x's and y's. We want to turn that into polar by turning those x's and y's into r's and thetas. First thing I'm going to do, I guess, is go ahead and just substitute. If I have an x, I'm going to replace it with an r cosine theta. If I have a y, I'm going to replace it with r sine theta. 2r cosine theta minus 3r sine theta equals 5. Now that's not very pretty, and I'm not going to promise that it is going to be pretty. But one thing to consider here is like once I do that, am I done or do I have to do more? You know, like when we put things into slope-intercept form, linear equations, we always want it to be like a y equals. When you type things in your graphing calculator, you go to the y equals screen. If we're in polar form, it's not y equals, it's r equals. You will want your final step to always be an r equals something. That means I'm not done. This is awfully fancy. I need to get the r by itself. What I'm going to do is I'm going to factor the r out. And then I'd have a 2 cosine theta minus 3 sine theta equals 5. And to get the r by itself, I'm going to divide by that big mess. And my final answer is going to be r equals 5 over 2 cosine theta minus 3 sine theta. Not pretty, but very doable. Now, if I were to type this in my calculator, and again, we'll do it tomorrow, we'll look at what that looks like on a polar graph. But what it's going to do is it's going to look just like this. And when I look at this, I know that this is a linear equation. So somehow or the other, when I type that in, it's going to look like a line when I do it. Now, just like when we deal with the rectangular coordinate system, there's certain types of equations that pop up for us a lot. We have our linear equations, and then we have these quadratic equations, and we have some rational equations, exponential. All right, same deal with polar. There's certain ones that come up a lot. And so what I'm trying to do is like one of each type that you're going to be coming across. So make sure you have, I'm only doing 3 because we're going to kind of focus on 3 special types. So we've done like one that comes up as a horizontal line. We've done the one that just comes up as some sort of linear equation. Let's look at this one. This polar equation is pretty simple. It's just r equals 4 sine theta. I have to somehow turn this r and this theta into an x and a y. Usually what that means is if I'm going to try to turn that into some kind of an x and a y, then I would like it to say r sine theta or something, and then I'd replace it with a y. That's what happened last time. If it said r cosine theta, I could replace it with an x. But it's not r sine theta, it's 4 sine theta. That's not the same deal. So how do I make that be an r sine theta? Well, I sneak in an r right there. I'm going to take it times r. But if I take it times r there, I have to take it times r over here. This ends up looking like r squared equals 4r sine theta. Remember what I wanted? I wanted it to be this. Hey, looky, I've got that now. It's r sine theta. Let's get rid of that r sine theta. That's going to be 4y. But not only do I need to get rid of the theta, I need to get rid of this r right here. And actually, I helped myself out by multiplying both sides by r, because now this r is an r squared, which works really nicely. For our Pythagorean one right here, r squared is equal to this. I'm going to replace that with an x squared plus a y squared. Now, what type of equation do you suppose this is? It's not linear. It's not a quadratic because it's not just the x that's squared, it's the y that is also squared. This is a flashback back to college algebra. Back to, well, farther back than that, back to geometry. This is a circle. Actually, it goes back to your conic sections that you did in college algebra when you have just an x squared and a y squared. That's a circle. What that means is I want my equation to look like something I'm familiar with as a circle, and this is not it. Like I said, it's going to be a flashback to college algebra. Here we go. We have to complete the square on this to convert it to something that looks like a circle. Maybe I should start with a little refresher where we're headed. This is what the circle equation looks like. X minus h squared plus y minus k squared equals r squared. That's what I want it to look like. I'm going to have to complete the square to make that happen. Let's start off by moving the 4y over with the y squared. You get everything on one side, x squared plus y squared. I'm going to subtract the 4y plus, and then I leave a blank space because I'm going to be completing the square. And when I do that, it's going to end up equaling 0 because I moved the 4y. X squared, I don't have anything to complete the square with. It's going to be by itself. It's done. But this right here does complete the square. Remember, to find out this number, you take half of this and square it, and you put it right there. Half of -4 is -2. Squared is 4. If I put a +4 there, I have to put a +4 on this side also. The whole point in completing the square is that this trinomial factors nicely to a binomial squared. Y, and you use this same sign. It's going to be a minus. And then what it would factor to is y minus 2, y minus 2. It's basically whatever I squared to get this number, which was the 2. Right here, I'm always putting this half of this number. When I did half of this number and squared, that half of this number is what I put right here, which was -2. You can always pull that out if you're nervous, you're not sure how that works, but that's the gist of it every time. Equals 4. This right here is now in this form. Remember that the HK is the center, the R is the radius. If I wanted to plot this circle, the HK would give me a center of 0, 2, and the radius would be 2. It would look like this. Over 0, up 2. That's my center. Radius is 2. That means I got to go out 2, all directions. And so it creates some kind of little circle like that. Regardless of whether you're on your rectangular, nice grid that you're used to, or the new polar graph, it's still going to look like that very same circle. All right, that's the fanciest equation we have. The others tend to be linear. This one's a little fancier. Everything we've done up till now is really based on those 4 rules, getting familiar with those 4 rules. And most of your assignment is that. Though there's a reason we're doing all this, there is nice application for polar coordinates. When you see that polar graph, you should kind of think of the radar. Have you seen that like in movies where they have that beep, 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 there's that green screen of the radar deal? That's what that looks like. Well, it actually is used in radar tracking. The distance and direction of a ship is often given in polar coordinates. If the radar detects 2 airplanes at the same altitude, okay, so these planes are in the same altitude, we got to be a little careful they don't crash kind of thing, right? That's what the, okay, I kind of got the direction of a ship and yet I'm doing airplanes. Okay, my bad, sorry. Works for ships and airplanes. Let's say we've got airplanes. Okay, We don't want them to crash. So the control tower is looking at their coordinates. Their polar coordinates are 5 miles, 110 degrees. So let's plot that. That's what my little dot is telling me to go ahead and plot that point. So 110 degrees is going to be over in the second quadrant. And you're 5 miles out, so that would be 5 rings out. I'm just going to estimate it to be right here. And then let's plot our other plane. Our other plane is only 3 miles out at 40 degrees. That's going to be closer to the pole, but at a 40-degree mark, I don't know, I'm going to guess right here-ish. The question is, how far apart are those planes? Well, we're used to doing like distance formula, but these are not X and Y coordinates. Now, I could, I suppose, if I had to, go convert them all, but I don't really have time to do that every time and not going to on a test do a bunch of conversion constantly. We want to be able to work with the polar coordinates in the form that they are. Think about this. Let's use what we already know. I've already hinted. Use the law of cosines. Well, the law of cosines works with triangles. I must need to have a triangle. I'm looking for this distance right here. So let's create a triangle from the pole. So, because I know this distance right here, that's how far out that was. That was 3 miles. This distance here was 5 miles. And I'm looking for this right here. This, I don't know, let's call it X, I guess. Now, I've already hinted that we're going to use the law of cosines. But we got to have 3 pieces of information for that, and all I have written is the 3 and the 5. And I'm looking for the X. I need one more piece of information. And I bet you, if you thought about it hard enough, you could figure out what this angle right here is. Do you know what this angle in my triangle would be? This is 40, so this one must be 50. And then my angle here was at 110, so that's 20 degrees past the 90. So 20 and 50, that's a 70-degree angle right there. If that's 70, I have enough information to do my law of cosines. Law of cosines, remember, out at the end you write cosine theta, which is going to be cosine 70. And when that's the case, the side that you're looking for is always across from it. This is going to end up being an x squared equals 3 squared plus 5 squared minus 3 times 5 times 2. Cosine of my angle is 70. This is where you just enter this in your calculator, left to right. I've conveniently already done that. I get x squared equals 23.74. But then, of course, I have to square root both sides. I get x to equal 4.87. That is the length of that side, which is really the distance between the two planes. Go ahead and label that in miles. And we've got that. A great way to go ahead and start tying together what we've already learned with these new polar coordinates that we're learning. All right, go have fun.